Artificial neural networks. Build a neural network. Artificial neural networks, ANNs, are a powerful tool for handling massive datasets, particularly when traditional machine learning algorithms fall short. ANNs are inspired by the structure of the human brain, consisting of interconnected layers of neurons. These layers include an input layer, one or more hidden layers, and an output layer. When the network includes multiple hidden layers, it is referred to as a deep learning neural network, which is especially effective at identifying complex patterns. For example, to create a neural network that determines whether an image contains a dog, we would use a process known as binary classification. The image, represented by its pixel data, is input into the network through the input layer. Each pixel serves as a data point and is processed by the neurons in the hidden layers. The neurons use activation functions to decide whether to pass the data to the next layer. This feed-forward process continues until the data reaches the output layer, which classifies the image as either containing a dog or not. The strength of ANNs lies in their ability to self-tune through supervised learning. As the network is trained with labeled data, it adjusts its internal parameters to improve accuracy, much like a musician fine-tuning an instrument to achieve the perfect note. The network ultimately produces a probability score that reflects the likelihood of each possible classification. This adaptability and ability to learn from data make ANNs an essential tool in modern data analysis and pattern recognition. Weighing the connections. As humans, we instinctively evaluate data by assigning significance to different elements based on our experiences and intuition. Consider, for example, looking at a photo of a lush, green field. If you spot a small, blurry shape in the image, you might assume it's a dog because dogs are commonly seen in such environments. Now, picture the same scenario in a barren desert landscape. Your likelihood of guessing that the shape is a dog decreases. Our brains naturally apply this kind of weighted reasoning, favoring certain outcomes over others based on context. Artificial neural networks operate in a similar manner, assigning weights to various inputs to improve predictive accuracy. Just as a musician adjusts the tension of guitar strings to achieve the correct pitch, neural networks fine-tune the weights between neurons to enhance their performance. In these networks, each connection between neurons has an associated weight, and these weights determine how strongly one neuron influences another. As data is processed through the network, these weights are continually adjusted, guiding the network toward more accurate predictions. This iterative tuning process is what enables an artificial neural network to learn and refine its ability to make decisions, much like a supervised machine learning model that starts with a training set and gradually improves its accuracy through repeated exposure to data. Initially, the network assigns random weights, but with each iteration, it learns from its mistakes, honing in on the most effective weights to produce reliable outcomes. The activation bias. An artificial neural network can be likened to a self-tuning musical instrument, constantly adjusting itself to produce the correct output. It works by comparing its predictions to the desired outcome and then fine-tuning its internal parameters to minimize errors. Despite its complexity, an artificial neural network is fundamentally a machine learning model, employing familiar techniques to improve its accuracy over time. It adjusts the weights between neurons, which can correct for variance in the data. Imagine trying to consistently hit a bullseye with darts. The network throws a dart, measures how close it is to the target, and then tweaks the weights before trying again. This iterative process is a delicate balance between bias and variance, known as the bias-variance trade-off. The network introduces bias, a value assigned to each neuron, to shift predictions in a way that minimizes overall error. However, tuning the bias affects variance, creating a constant push and pull as the network seeks the optimal balance. It's a bit like trying to adjust the position of the dartboard while still aiming for the bullseye. Overfitting can complicate this process, as the network might become too finely tuned to the training data, making it difficult to generalize to new data. Overfitting is like learning to drive perfectly on a specific route but struggling when conditions change. The neural network must continuously adjust, trying to avoid overcorrecting in either direction, too much bias or too much variance. The key to effective tuning lies in understanding that bias is applied to the neuron after variance adjustments, like moving the dartboard only after the initial throws. This sequence is crucial because the network needs to see the pattern of errors before it knows how to correct them effectively. Improve accuracy. Learning from mistakes. Human thinking often simplifies decisions into right or wrong, with little room for nuance. However, artificial neural networks operate in shades of gray rather than black and white. To a neural network, there's a significant difference between being 95% right and 97% right. The key challenge lies in how the system quantifies and responds to its errors. In neural networks, this is done through a cost function, a numerical value that represents how far the system's prediction deviates from the correct answer. For example, if a neural network predicts there's a 97% chance an image contains a dog, but the image is actually of a cat, the resulting error will have a relatively small cost. On the other hand, if the network predicts a 99% chance of the image being a dog, but it's actually a snow-covered mountain, the error, and thus the cost, will be much larger. The system uses this cost to adjust its internal parameters, such as weights and biases, in order to improve future predictions. To make these adjustments, many neural networks rely on a method called gradient descent. This process can be compared to throwing darts at a dartboard. The angle and distance of each throw are adjusted based on how far the dart lands from the bullseye. If a throw misses by a wide margin, the adjustment will be more significant. If the throw is close, only a slight adjustment is needed. In a similar way, the neural network uses gradient descent to fine-tune its parameters, correcting more drastically when it's far off the mark and more cautiously when it's close. This process is known as backpropagation, or backprop for short, and it's a fundamental technique in training neural networks. Essentially, while the data flows forward through the network, errors are propagated backward to refine the system's accuracy. Through this cycle of forward predictions and backward corrections, the network gradually hones in on the right answers. Step through the network. Building an AI system requires a systematic approach, especially when tackling a task like identifying dogs in images. The first step for data scientists is to determine their objective. Here, it's about classifying data into two categories: images with dogs and those without. This binary classification problem is handled using supervised machine learning, where the system learns from a labeled dataset. In this case, the AI is trained on thousands of images that are known to contain dogs. The data scientists then decide whether to use traditional machine learning algorithms like k-nearest neighbor or naive Bayes, or opt for a more complex artificial neural network. Given the intricate nature of image data, a neural network is often the preferred choice. They'll design the network with an input layer, hidden layers, and an output layer with two nodes, one for each category. The network is then initialized with random weights and biases, preparing it for training. As the training images are fed through the network, it makes predictions, which are then compared to the actual labels. If the network misclassifies an image, it adjusts its internal parameters using techniques like backpropagation to improve accuracy. Once the training phase is complete, the network is tested on a new set of unlabeled images to evaluate its performance. If the network performs well on the training data but poorly on the test data, it may be overfitting, meaning it has learned the training data too well and lacks the generalization needed for new data. While classifying images might not be your immediate task, the principles of binary classification can be applied to various datasets, from customer profiles to sales data, offering valuable insights through AI. Where to go from here? Using AI systems. Artificial intelligence, AI, has evolved significantly since its inception, starting with early systems like the general problem solver, which relied on symbolic logic to program responses directly into a computer. However, the landscape shifted rapidly after the first AI conference in 1956, leading to the emergence of machine learning. Unlike earlier systems, machine learning models analyze data to identify patterns and improve their performance over time. Today, AI systems are becoming integral to the workplace, addressing complex challenges and even generating innovative solutions. This makes it crucial to grasp how these technologies function. Interestingly, most people interacting with AI won't be data scientists but rather business professionals and entrepreneurs. It's likely that in the coming years, you'll find yourself involved in an AI project. Just as managers today collaborate with software developers, they will soon work alongside AI systems and data scientists. Consider a scenario where someone on your team presents a report stating, "Managers must set clear goals, evaluate outcomes, and provide feedback for AI systems." Like any other technology, AI requires effective management to thrive. There are a few key points to keep in mind. First, the quality of an AI system is only as good as the data it's fed. This data must be accurate and reflective of reality, or the system will produce flawed results. Second, AI learns through experimentation, which involves trial and error. Managers need to be patient and allow the system time to learn and improve. Finally, while AI can process vast amounts of data and uncover patterns beyond human capability, it still requires oversight and guidance. With these considerations, business professionals can start planning how to integrate AI into their operations. They can think about the challenges they want to tackle and how AI might offer solutions. And here's a surprising twist. Most of what you just read was generated by an AI system called GPT-3, Generative Pre-trained Transformer 3. This AI analyzed millions of articles on artificial intelligence and business applications, then synthesized common patterns into coherent text. As AI continues to advance, it will become increasingly human-like, and the organizations that succeed will be those that enhance, rather than replace, human creativity. Applying AI to solve problems. In this course, you explored the foundational technology behind artificial intelligence. We began with an introduction to early concepts like the general problem solver and symbolic reasoning, and traced the evolution of machine learning from its modest beginnings to its current status as a leading force in AI. You gained insights into various machine learning techniques and how they leverage vast datasets to uncover valuable patterns. We also delved into artificial neural networks, examining how they enhance machine learning by identifying intricate patterns through deep learning. Finally, we covered how networks utilize backpropagation to refine their accuracy by learning from errors. I hope this course has provided you with practical insights on applying these technologies to tackle complex problems and encouraged you to reflect on the ethical implications of AI. Consider the impact of automated decisions on personal aspects like health, welfare, and financial matters, especially when the process is opaque. For those intrigued by these ethical considerations, I recommend checking out my data ethics series. Feel free to connect with me on LinkedIn for more articles and discussions on AI, data ethics, and business challenges. Thank you for participating in this introduction to artificial intelligence.